Okay. Are we recording? Okay. So I forgot that there is another good news, bad news today, and that's one of those today. Okay, so
I'm okay with that.
we'll do some cool demos, but you don't have any homework.
Yes!
That's a win.
Coachella tonight!
Yes, and it's homecoming tonight.
$1.
Man, you are just the best.
Yes. Maybe he'll forget about other ones too.
Where did you get it?
For the hour.
Okay, anyway, not relevant. Okay, so here's the next big thing, and this is forces. So if you look at how this thing has been structured. So the first thing we did is we figured out how to do physics. Okay, meters, kilograms, seconds, dimensional analysis, how we graph stuff. Then we used that to figure out, okay, vectors. That led into velocity. All right, that's cool. Then we figured, okay, if we want to change velocity, that's known as acceleration. Okay, so now we got acceleration out of the way. So now we need to look at forces. So the simplest definition of forces is that it's something that's, now here's the key word, capable of causing an acceleration. Okay? That doesn't mean that it's necessarily going to cause an acceleration. It's that it's capable of causing an acceleration. Okay? So one of the first things we need to look at is the kind of a historical perspective on how this whole deal played out. So this whole idea of motion, actually if you look at the history of science, this whole idea of motion and inertia and Newton's first law of motion actually goes quite a ways back. So up here on the board, I've got a statement that's written that says inclinatio ad quiddum. Okay? So if you're a little bit rusty on your ancient Latin, basically it means an inclination for being at rest. Okay? Or an inclination for being quiet. So this whole idea of motion and what it is and what it isn't actually goes all the way back to even Aristotle. So Aristotle believed in all objects have a natural state of motion. So here's how Aristotle viewed it, this inclinatio ad quiddum, is that if I take this remote and I give it a push, okay, what's it going to do? Well, but as soon as I stop, what's it going to, as soon as I stop pushing it, what's it going to do? Stop, right? If I take this golf ball and I drop it, every time, what's it going to do? It's going to stop.
So then why do we
just
getting there? Thanks for being good today.
Okay. So, and this could be the lab that we would do. Everybody, I'm not going to do this because it's just going to be annoying. Okay? But I said, okay, everybody, drop a golf ball. Watch what happens. Every time, what's it going to do?
Stop eventually.
It's going to stop. Okay? Inclinatio ad quiddum. So, Aristotle says, look, the natural state of objects in motion isn't to be in motion. The natural state for them is to be at rest. For about 2,000 years, that was the dominant thought. So, if you want to keep something moving, though, for example, if I have this remote and I want to keep it moving, what do I have to do? I have to keep applying the force, right? Because as soon as I stop applying the force, it comes to rest. So it's kind of like you guys at 6 o'clock on a Saturday morning. What's your natural state of motion? At rest. Okay? Probably more so than about any other day of the week, 6 o'clock on a Saturday morning, your natural state of motion is to be at rest. Now, Mom realizes that Aunt Martha is coming over at 7 o'clock for brekkie, and the house is a disaster, right? Brekkie. So, spotty. So, Mom says, or Mom says, get your bum out of bed and start doing some cleaning. Okay? So, yeah.
Get your bum out of bed.
No, you wouldn't be able to quit laughing. Okay, anyway, now,
Get in the shower and
what's the only way that your mom is going to keep you cleaning? Is to keep yelling. Because as soon as she stops applying the force of yelling, what are you going to do? You're going to stop, sit on the couch or the recliner or lay on the floor. You are going to come to rest. Because that is your natural state of motion at 6 o'clock on a Saturday morning. Laura, does this get a big nod from you? Yeah. Okay, all right. And it's true. So this is, and for 2,000 years, everybody says, hey, that's cool, right? Everything comes to rest. Now, we'll talk more about this later, but he viewed the heavens as a different idea. So you look at the motion of the stars, of the planets, the moon, the sun, okay? Those tend to move in circular paths. So he said, okay, their natural state of motion is to actually travel in a circular path. So the heavens, their state of motion is to be in motion, but to move in circles. Because remember, at the time, it was the freshman mentality that we were the center of the universe and everything revolved around us. Okay? So they said, okay, they're moving in circles because it isn't like the sun stops halfway through and says, screw it, I'm done. Okay? Or I'm just going to sit here. No, that would be bad because we get really, really hot really, really fast. The other side of the earth would get really, really cold. So they said, okay, the natural state of the heavens is in circular motion. Everything on earth, its natural state is to be at rest. And that made sense. Everybody was cool for about 2,000 years. So along comes Galileo. So Galileo has a different idea. He says, okay, what if we take away friction? So, hold on, just grab something. Just charge it right now. And no, you guys don't get to play with this. No. Bad things would happen.
Fun things.
No, bad things would happen.
Depends on your definition of bad.
Oh, it didn't charge. No. Okay, imagine this is a little hovercraft that has no friction. Okay? I know, I'm bummed. I had it on charge and the battery didn't take a charge. Okay, so imagine this is a frictionless surface, which is really, really cool because you can kick it and it slides forever and ever and ever. So, it does. I mean, literally. And that was supposed to be charged and for whatever reason it didn't charge. Okay.
Charge it right now. So
yeah, can we charge it now? Make sure it's
No, it was plugged in all night.
So then why isn't
I don't know. Okay?
It's the age-old question.
No. It was this is the battery that was charged.
Maybe it's a bad outfit.
Okay, maybe it's a bad battery. I don't know. Okay, but anyway, so here's the point. So imagine this is a frictionless surface. And I give it a push, and it's just going to keep going. So Galileo says, whoa. There's nothing magic about something coming to rest. The only reason that it comes to rest is because of friction. If you neglect friction, it will continue to move in a straight line at a constant speed until an outside force acts upon it. So Galileo just basically takes Aristotle and says, you're right, but there isn't something magic about a preferred state of rest. The state of motion it has is whatever state of motion it wants to be in. So if you can alleviate friction, and this is Newton's first law, the law of inertia, that it says, okay, it's going to maintain whatever state of motion it has. Now, here's two important parts to this. It wants to move in a straight line at a constant speed. Okay, and there's two parts to this. So, a straight line at a constant speed. So basically, whatever the velocity vector is at any given instant is whatever velocity vector it wants to maintain. Now, and that's true of us, it's also true of light. So, and this is what we'll show with the Fresnel lens. We'll go outside, assuming the sun is still shining. So, if I take my glasses and I hold them up here, right, a distance away from the screen, even though I can look and see all of you through them, okay, but if I hold them up to the screen, it casts a shadow. But if I bring them close enough, then it goes clear. So, all...
Hold up. I've never seen that before. Why?
Okay, so I'm here, right?
Yeah.
Then,
Sunglasses. Screw physics, man. You're a magician.
Yeah, right. People will pay thousands of dollars each night to see me go like this. Okay, so basically what happens is that the photons that are emitted from the light, they want to travel in a straight line. And they continue to travel in a straight line until something impacts them. So what the lenses do is that the lenses work by changing the path of the photons. So basically what happens, the reason that it appears dark out here is because where they're focused is so far away from the screen.
And then the lighter.
Yeah, and then when I get close enough, basically you're inside the point where the light is being focused. And that's why it's clear when it's here, but it's dark out
And
here.
those little light spots are where the photons are going.
Yeah. Okay, now the other thing that you can do with light, so here I've got just canola oil, and it's just a test tube, okay? And so what I'm going to do is, and light is actually fairly complicated, so if you start at the beginning, what's allowing light to be emitted from the bulbs in this room? Oh, I'm going to go beat all of your Chem 1 students, all of your Chem 1 teachers.
Wait, repeat the question.
What is
jumping of
allowing
electrons.
light to be emitted from the bulbs in this
The
room?
jumping of the electrons from levels, and then it releases photons.
Okay.
Yeah.
Releases photons.
Excited photons and all that good stuff. And
Okay.
electrons, neutrons.
Photons,
Well, you said,
electrons,
well, you said
persons,
from the beginning.
protons.
I thought you were talking about like since the beginning of time.
It's all tons, persons, whatever.
Persons.
That's good.
Okay, so anyway, so it basically goes back, and you can understand a lot of science if you understand one idea, that nature is a lazy prima donna. These photons are only being emitted because the electrons are being excited, they're at the ground state, they jump up to higher energy levels, and they come back down. And that gets really weird too, because the electrons don't even exist in between the different quantum levels.
Okay, yeah.
They don't.
So
So
they're
it's
like-
don't know. That's a whole other discussion, and you end up doing drugs. You can't talk about this right now. So, but if I go turn off the light switch, right, nothing happens, because they say, screw it, we're just going to chill out, okay? We're going to be at rest. We're not going to jump energy levels, because it isn't like the electrons go, wow, I really like kicking off photons. And so even if I shut off the light, it isn't like some of them go, oh, I'm just going to keep doing this. I'm excited. Wow, I had caffeine. I'm going to keep bouncing up and down even though the electricity is off. No, they all stop, okay? Because at that point, nature goes, I'm just going to chill. I'm at the ground state. This is where I'm at. I'm not going to jump energy levels. You throw some electricity to it, hey, we'll start making the energy jumps. We'll start kicking out photons. Don't think about that process too much, about how a very, 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 very tiny bit of matter can exist from one energy level to the next, and then it returns, and it magically somehow kicks off this bundle of energy that is emitted, and then it hits, you know, Kendra's shirt, and oh, it's purple. And then it bounces off that. I see it as purple.
Yeah, I think that's wrong. I only devote my life to finding.
Well, here's the thing. How can something just transport? How can it just?
Oh, it gets weird. We'll get we get so okay. All right. So here's the deal. So if you look at what allows you to see this test tube inside of here, so these photons are all bouncing off. They're going through here. They're hitting the test tube. They're passing through it. They go through the other side. Your eye hits it, and by the way, everything you're seeing right now is actually upside down because of the type of lens that's in your eye. Okay, but your brain says, "Oh, that's really weird. I want to flip it upside down, or otherwise you're looking at the world
I was
like
at the
this."
eye doctor shadowing, and he explained the whole thing to me too. It was really cool.
Yes.
Yes.
Yeah. So the
Yes.
human body is an amazing
It's
thing.
really cool.
It is. So now, I need you some assistance. Okay. So I just need you to hold that upright. Okay.
Should we zoom?
If you can.
All right, Casey, Dan.
All right.
Hunter,
Hey.
Hunter was on mine. I'm gonna get one of those
Now,
three
if
students
you're
to
at the
follow.
back, you might get a little bit closer because it's easy to see if you're not.
That's what I'm calling.
So, I'm gonna just
Don't
take
pour
this.
it on me.
I'm not gonna pour it on you.
How close are we looking?
It isn't like it's going to explode, but it's easy to see if you're a little bit closer.
You need a funnel.
No, I'm good. Okay, you ready? So, focus on the test tube.
I can't see the test tube. Understand?
Focusing on
It looks clear.
Whoa.
Oh,
It's clear.
what?
Like the top of the test tube looks clear.
Okay?
No, the bottom.
So, if you're up here, you can see it. Then it.
Oh, it's invisible.
You
You are a
Okay?
magician.
I am. I am. So, basically, what happens.
Camper Houdini.
Stanley Burke.
The science guy. I should have my own show. Okay, so basically what happens is this. Oil and Pyrex has the exact same what we call index of refraction. The light wants to travel in a straight line. So when it hits a certain material with an index of refraction that's different, then the light gets slowed down. Okay? And so then, by filling that up with oil and Pyrex has the exact same index of refraction. So the light, as it travels through, doesn't get bent. It travels through at the exact same speed. That's why it appears to disappear, because of the fact that the light isn't being sped up or slowed down as it goes through that medium. Okay? Now, speaking of harnessing the power of light, let's go outside. Now, well, keep it going for a second.
We've been good.
So what we're going to do is we're going to use this, okay?
Explain the physics behind that is the best thing.
Stand behind it.
I want a picture. I want a picture.
Okay.
Okay, I want to see what I look. Can I see what I look like?
Hold on.
Wait,
Hold on.
make sure the middle of it is at
wait.
your head. Like, make it stand.
Hey, let me get it.
Like what?
Lift it up and make sure your head is in the.
Yeah, perfect. Right there.
No, make sure your head's in the middle.
I'm glad I made your day. Are we good now?
Wait, I want to see the picture.
Okay, are we good?
Yeah, we're just
Okay, so what this is known as a Fresnel lens, and it was actually developed to work in lighthouses. So lighthouses, you wanted to obviously have a bright light. So what would happen is that you have behind here, you would have like your source of your light, lantern, whatever. So then the Fresnel lens is that it takes that light and magnifies it. So that's why I look so big, is because of the fact that it's taking that image and making it look bigger. So the light wants to travel in a straight line, it hits this, it gets accelerated, and it appears differently.
So do we all look funny when you stand behind there?
Yeah. I mean, I don't know. Yeah, you look like really big right now
I'm
and far
nervous.
away. So what we're going to do, we're going to go outside and we're going to reverse the process. And we're going to take sunlight and focus it down to a point and see what we can do with various things. So if somebody has a wooden pencil that they're willing to sacrifice,
Got one right here, Mr. Burkamp.
maybe a piece of gum and a couple of pennies.
Do you want a chewed piece of gum? Or
No, I want
just a piece of gum.
Okay, so take the camera.
I actually want.
Oh my god.
Can't see it.
That hurts my eyes looking at that.
Yeah. So basically, and it's cool to think about it. So the photons that you're seeing right now left the sun about 8 minutes ago. And they're just hitting this rock that we're on. Just enough cloud cover that.
Oh.
I'm saying it's pretty bright.
I gotta stop
Oh, that's hurting.
Oh! Hold on. We'll just kind of torch it. We'll just kind of.
No. Do you need the wrapper?
Nah, we'll just melt it down.
We'll just literally.
Just enough cloud cover.
Am I in?
You're all right.
Yeah, Kendra, you're kind of blocking our sun.
I gave like 10 pieces of gum out within a matter of 2 seconds, so.
Oh yeah. Oh, that's a good one. Oh. Oh yeah, that'll burn it. Oh my god. Wowzers.
Problem is that gum really doesn't.
Eric, put your hand underneath there.
Yeah, really one. It's probably not even that hot.
I dare you to put your hand underneath there.
Let's just burn it.
Do it, Eric.
Do it, Eric.
No,
wait,
I
wait.
was kidding.
How hot is it? Wow! Oh wow! I swear that was hot.
Did you get that on camera?
This burns this.
I wasn't. Okay, where's the pin?
Our gum's looking pretty melted.
It felt like I put my finger on it.
Okay.
I swear.
Better save that video.
UV rays are out. Me too.
Yeah, where's my SPF, bro?
Thanks, I was really stressing out about that, Hallie.
Look at that.
About that wrapper. Don't litter.
Oh!
Oh man.
Oh, yeah.
Oh snap! Crackle pop.
Oh, that. It's doing it.
Are you feeling me up?
The wind is killing.
We're camp.
What?
I found something else we can burn.
What's that?
Try and kill a frog with that. Burn this.
Oh, it's smoky. Have you seen the?
Oh, let's burn the frog.
We're not burning a frog.
It's a noble cause.
You're a better person than Reese. We just actually. Where's the wind coming from?
Do you see it like smoky?
I think blind people see
Okay. So yeah.
Who wants the gum now?
Yeah.
No, dude.
So it made a nice burn mark on the pencil. So who's got the pennies?
That was my
Me.
pencil.
There, keep that forever.
I will. That's my pencil, Kyle.
I took
Should
it
have
from you.
birthday
I'll see it.
Okay.
Let me see it.
There's a penny shiny.
Now this gets bright just because it reflects off of it. But here's the cool thing: is that okay? This isn't like this big of an area. Okay, it's about 2 feet by 3 feet, and we're taking just that energy, and the photons are just hitting this, and we're able to very easily burn a hole in the pencil. So these photons that you can't see are carrying a tremendous amount of energy. All this does is focus out all that energy into one point. So if this goes like it should, and I'm not sure because it's cloudy, I should be able to melt the zinc that's inside the pennies. We'll see. Can somebody actually hold that side so I'm not in this?
Get those crocs over here.
You gotta get.
I don't care, I'll move.
I know, we're trying to figure out.
Get it focused.
Just move it more towards the ground. Trust me, I burned a lot of hands as a kid.
Yep.
With the magnifying glass.
Is it gold?
No, it's just reflecting a whole bunch of light.
It's silver.
It did turn it.
I would burn their head.
Back in my day when I had Crocs, I love this.
Can you push my hair out of my face? Thank you. You can tuck it by my ear if you want to.
No, hold it.
Thanks.
I'll burn my hand if there's
No, you're not going to burn your hand. Here, let's move that just a little bit. There we go.
Perfect. Do not hurt that frog.
Don't do anything to the frog.
Go wash
Step
your
away from Kermit.
Oh, my hair went in my face again.
So what is it supposed to be doing?
Well, it's going to get hot enough where we're going to boil the zinc inside, but I don't know if it's just cloudy enough that it's not getting hot enough. Because it'll actually fuse the pennies together. James?
Maybe it's always here.
What? I wasn't even over there.
Where you're standing.
I don't care,
now.
I'm still guilty by association.
Over there, wherever that was happening.
You're defacing national currency, man. That's not okay.
So why don't we use this as a way of powering?
It's still a crime.
You're still
Something.
It is, it's called solar energy.
No, I don't mean with solar panels. I mean with like, get a big lens.
They
and-
do. They use it. We'll talk about it. But basically, the new process is that you focus this all into one point and you melt sand. And then as the sand cools at night, it runs a turbine which generates electricity, and that way you have energy at night.
Oh, cool. For your turbines.
It's just not good.
So could this like
So-
boil water?
Oh yeah, there's actually whole cookbooks written. They're really, really hot though. So there's actually whole, and by the way, if you stand by this, it'll catch your pants leg on fire because I did that last year.
Yeah.
Oh my god.
No, I did. I was just I just reached across like that, and the beam caught my cuffs on fire, and the kid's like, "You know your pants are on fire." Really? Real matter of fact, it's like not a big deal. Anyway, so what should have happened, but there's just enough cloud cover to screw everything up.
Tomorrow or Monday?
But it'll actually like fuse the pennies together, and it'll get hot enough to boil that zinc that's inside. So it's kind of cool. You take all these photons that are hitting this, focus that energy into one point, you can boil
My
metal.
eyesight going crazy.
It's probably cold enough. Is it still warm?
Oh yeah.
Okay, all right, so, yeah. That's a bright light. Okay, so, and this is the cool thing about it. It's like, okay, so here are these photons, these little bundles of energy that were emitted from the sun. Took 8.3 minutes to get here. We take it, we focus all of them into one small point, and as you guys can attest, the metal got really, really hot. Not enough to really boil it, which normally, if there's no cloud cover, usually within about 30 seconds, those pennies will like boil and they'll fuse together.
So we're doing this tomorrow.
So,
It's supposed to rain.
We're
yeah, it's
getting
supposed
these
to rain.
pennies boiled.
Tomorrow's gonna be
okay,
rainy
well,
day.
if it's sunny,
If it's sunny
if it's
Sunday,
sunny one day, we'll go out and we'll try.
I can't tell if there's.
Okay, so when physicists started to look at this whole concept of all these different forces, they said, okay, hey, we need to sort this out. And they said, okay, well, let's just make a list of what we call the 4 fundamental forces. So the first one's easy, okay? That's gravity. So that's the one that you're familiar with. Okay, this is the one that directly or indirectly impacts you every day of your life. And we'll spend a lot more time talking about this. And don't worry about this for now. We'll do this calculation, and we're just not going to do it now. But basically what this is big G was known as the universal gravitational constant. It's just a number. Don't worry about it. It's just a number. And then you have 2 masses, and then you have the distance between them. So what this means is that any 2 objects that have mass are gravitationally attracted to each other. So right now, you're obviously gravitationally attracted to this rock that we're on. You're gravitationally attracted to the sun, to Neptune, to Saturn. You are gravitationally attracted to the most distant electron on the other side of the universe. So the only way that you can be in zero gravity is like the freshman mentality that you are the only mass in the universe. If there's any other mass in the universe, you cannot be in zero gravity. Okay? So, you know, if you see footage of the astronauts floating in the International Space Station, oh, they're floating because they're in zero gravity. No, they're not. Okay? No. They've got to be in a gravitational field, or they'd go flying off into space anyway. So, all you have to realize is that if you have really, really big masses, like the Earth and the Sun, and as the distance between them gets bigger, the force gets smaller. Okay?
What, so the force is just Newton's?
Yeah, it's just in newtons. Okay? Now, a couple of unique things about this. First off, it's never repulsive. It isn't like I have to wake up one morning and go to get out of bed, and then gravity is going to be pushing me up towards the ceiling in the house. Okay? It's not. When I drop something, I promise you, it's going to fall towards the center of the earth. Okay?
That will never change.
Huh?
That will never change.
We've never known it to change because it
Well,
would
as
be
a
really,
kid-
really weird. What?
As a kid, like somebody asked, like, imagine if there was like gravity just got turned off, and it's, every day I'd like panic that like we'd fly.
Oh, I'd kill for a gravity switch in my room.
No,
be able
like
to turn it
then
off.
because then
Just in my
the
room.
houses would just and everything because there's so much force that are spinning and
Yeah.
oh, we would not be okay.
Oh, yeah, bad things to happen. But thankfully,
And I
it
always
doesn't. Okay.
got scared
That-
of drowning.
Okay.
In like
I
the
don't.
end of
Okay,
space.
look. This is not like a psychological discussion time. Okay, this is physics, not psychology.
Maybe
I'm just-
it'll never happen.
Okay, all right, you're good. Now, this is only attractive That's the only thing you really need to know. And the greater the distance between two objects, the weaker the force becomes. That's all you need to know for now. We'll spend a week dealing with this equation, just not right now. So the second one is what we call the electrostatic force. Now, this is the one that is the weirdest of all of them, okay? And actually kind of the least understood of all of the different forces. So, stop that for a second. I go get a balloon and we'll talk about weird things. Let's address it. All right. So, true or false? Every time something is going to accelerate, created by a force, the force has to actually come in contact with the object to make it accelerate.
True.
True.
Don't ask me why. I don't know why.
Okay.
You sound good. Like you
Yeah, like that discovery on like.
No. So true or false, does every force require a physical contact to cause an acceleration?
No. Gravity doesn't.
Gravity
No, not physical.
If I hold this up and I drop it,
Not physical.
is the Earth physically like hitting it down?
No.
No. Okay. So there has to be a carrier of information. It's like if I want to talk to you guys about forces, I can't do this. Okay? Please.
I can't learn without it.
I swear it is making
Better? Okay. All right. Fine. All right. So if I want to convey to you guys information, I have to convey that information across a distance. So the act of sound is actually fairly advanced. So if I want to say forces, okay, my brain has to decide, okay, we need to talk about forces. Then I make my vocal cords vibrate. I form the word forces, which comes out as nothing but a series of compression waves that go through the air. Those compression waves hit your eardrums vibrate. It transfers that information through the inner ear bones to your auditory nerve. Your auditory nerve sends a message to your brain processes and says, oh, Burkham's talking about forces as opposed to pumpkins. So even hearing something is a fairly complex situation. Now, could I have this conversation with you all on the moon in terms of just speaking?
No.
Why not? Ellie, why not?
There's no atmosphere for the sun to travel through.
Yeah, I can try and talk, but there's no medium through which it has to be conveyed.
Could you put
So-
your mouth up against the planet and then talk into that and then us?
Okay, but then I'm having a medium. Okay, so if I'm going to hold up this puck and drop it, and gravity is going to make it fall, there has to be a medium through which this is going to be conveyed. Because if there isn't, then I let go of it. Nature is a lazy prima donna. Nature says, I'm just going to let it chill out here. Because this puck, because of the first law of inertia, doesn't want to accelerate. It wants to stay here. It wants to maintain this state of motion. So gravity has to act through a medium. So if I take this balloon, so kind of, you need to move over so the camera can see through you. Or you can just lay down. Okay. So right now I've got this balloon, right? Not a big deal. So I'm going to take this, give this a rub, okay?
Would you like me to just put the camera on my desk?
No.
Okay. Now,
You're Darth Vader.
kind of Jedi mind trick thing going on, right? So I can make the balloon,
Whoa.
okay?
Wowzers.
Right? So,
Why have you not quit your job as a physics teacher yet?
but am I directly touching the balloon?
No.
No. But I'm conveying a force. So what has to happen in between?
A medium.
There has to be a medium, right?
Okay, so why are planets attracted when interstellar space is maybe one
Vacuum.
atom?
That's
Yeah.
what I've been
Well,
wondering
something
this whole
called
time.
gravitons, okay? Now, how this is working is actually an exchange of photons, which is the same thing that's carrying information in terms of like light. So basically, the short version of what happened is that this thing took a bunch of electrons off of the blanket. Blanket's now positively charged. Now, I'm not I'm not permanently positively charged. So here's basically what's happening, is that here's the balloon, and it's got a whole bunch of negatively charged particles on it. So electrons are these weird little things. This is getting hot. Electrons are these weird little things that basically don't make a lot of sense. They're all identical. Every electron we've ever studied is identical. It has the exact same charge of 1.6 times 10 to the negative 19th coulomb. Don't worry about that number, but they all have the exact same amount of charge. And then you have protons, which are these big massive particles. And the cool thing about protons is that even though they're much more massive, like it takes 1,800 electrons to balance out about one proton, okay, they're massive compared to electrons. The protons, which all are also identical as well, we've never found any variance on protons or neutrons, they're all the same mass. But the protons have the exact same amount of charge as the electrons do. But they're these big massive particles, and they're locked up in the nucleus. So basically what happens is this. When I bring my hand, okay, fingernail, up to it, my hand is composed of atoms, protons, electrons, neutrons. So when I bring my hand close, these electrons, which are like kind of like the little yippy chihuahua dogs of the atomic world, okay, and the protons are like the St. Bernards that are really chill and big and they don't move much, okay. So when I bring my hand close to this, my electrons, the little yippy chihuahua dogs, go, wow, there's other electrons. We're the same charge. We're out of here. So they flee to the other side of my hand. What's left behind? Protons. So when I bring my hand there, it isn't that my hand is permanently positively charged. It's just that when I bring it there, enough of those electrons flee, the protons are left behind, that it becomes attracted to my hand. So I'm not positively charged, I'm neutral. But I can make my hand, or a portion of my hand, positively charged, and that's why it becomes attracted to it. So, and they, you know, it's still there for after a while, okay? So, again, you look at, if something's going to accelerate, you have to have a force acting on it. Okay, so stop that, let's go to the back. Garfield?
Yep, ready.
All right, so I'm going to charge the balloon again, and everybody says, oh, gravity is this really, really strong force, okay? And it is, okay? Without it, we don't orbit the sun, we don't have stars, we don't have a whole bunch of things. But if I take my hand and move it over the paper clips, Jedi mind trick that this is, nothing really happens. The paper is attracted to my hand, but the paper is also attracted to this big rock that we're on, and it just stays there and goes, well, I'm kind of attracted to you, but really I'm just more comfortable here. But if I take the charged balloon and pass it over it,
Whoa.
That's gotta be one of the coolest
Someone
things
get
I've
a
ever seen.
steak.
okay? So, is the electrostatic force stronger or weaker than gravity? Stronger, because gravity is pulling it down, but the attraction is making it move up. So basically what's happening is the same thing that happened with my hand. When I put this big negative region over the top of it, one side of that bit of paper becomes negatively charged because the electrons ran away. That left the positively charged region, and so that became attracted to the balloon. That was stronger than the gravity pulling it down. Hey, it came up. Now, there's a limit, though, to what I can do. Because if I hold it up here, nothing happens because I'm too far away. So as I bring it closer, what happens to the distance? It gets shorter, the force becomes stronger. So as I do this,
See which ones are sort of strong ones.
there's a point there where that force becomes strong enough to lift those up. And if I could get if I could get it just right, and so you'll notice some of them kind of will almost hover for a little bit. So basically, if I can make Garfield, if I can make those just hover, basically the electrostatic force pulling up is just balancing out the gravitational pull pulling it down.
No, it's
Now,
zero
there's a-
G's.
Huh?
It's zero gravity. That's what it is.
0 G. Okay. Now the other thing you can do, put this here.
Oh my goodness.
Ooh.
That looks creepy.
Flower.
It's like watching
Yeah. How you going? Are you doing science?
We're doing the wave.
How to dance?
So, here's the question.
Yeah, this is really soft.
Why does it do that? What's happening?
Oh, some are positive or negatively charged, so they're going the other way.
Oh my
That's
gosh.
cool. That's neat. I like
That's-
that.
That's top shelf right there.
Just looking.
Okay, so,
This is gonna be a hit on YouTube. This
okay, all right.
This is probably
Because it's all about the dinosaur lab coat.
I say
And
you
without
actually
this, it's just.
It's just physics. That's all it is.
Okay, so now, when I do this, so why does that side, those actually want to go away from each other? Why?
negatively charged.
Yes, because all the electrons are fleeing each other. So even if I move it from on top, okay, right?
If you put it right on top, will all of them come up?
Well, problem is that as soon as one comes up, then it tries to equalize the charge.
Okay.
But you can get some of them. It's like this little Klingon thing, okay? Ow, sea urchin. All right, so basically what's happening is that you get this whole negatively charged thing going. All these electrons want to run away. That leaves the positively charged region behind. It comes up. Now, pop can. So if I said, I want to make the pop can roll, what are some things that I could do to make the pop can roll?
push it.
Push it.
I can push it, okay?
I said first, sure.
All right,
Blow it.
Push it.
There's your paper clips too.
okay?
You can suck it.
Bop it.
Now,
I bet I could.
hold on.
We're getting in a hole.
Hold on, the paper's in the way.
Come on.
Whoa. Look at that. It's like a little puppy.
So, what?
So can you put the balloon on the metal thing
So do you
and
have-
turn it on and give it a supercharge?
Well, but then it's just, no, not really.
So do you have positive or negative charges
Okay.
right at this?
So the balloon is negatively charged.
Alright.
So basically what happens is this. You have that region right around that can, that's closest to it. Those electrons have left. You've got the positive charge's nucleus left behind. That becomes attracted to the balloon. That's what makes it roll. Now, I could do it like this, okay? And that's still happening, but that's not enough to make the can levitate. So I can't make the can levitate, but I can make it roll.
What if you put it on top of it and set it to the side?
So if you put it on a scale, it'd weigh less?
A little bit. Not enough to really probably to be able to pick up much, but it would weigh a little bit less. If I had a sensitive enough scale.
What's behind the scale?
So if you're desperate for money in college, bet someone $5 that you can take a balloon and make a pop can roll. You just have to have a good source of static electricity. Now, you also have, this is kind of the mother of all things to generate electricity, what's known as a Van de Graaff generator. So we'll take some little bits of paper and put those up there on top. And give that a
Really
try.
fabulous hair.
Now the problem is it's humid and this doesn't work as well.
Oh.
Pretty good at making
Come on, get up to speed.
Trying.
noise. What happens if Coke in this right now?
Nothing, just get shot.
Okay. Come on, little Ham.
I really want to.
Ham-bone, do it, ham-bone.
Come on, Ham.
Come on.
Do it for the video, Ham. Do it for the video.
Hold on.
We're trying to get Stan.
I want to see a spark.
Hold on, and then after it. Oh.
Whoa, whoa.
Ooh.
Oh, look at that. That's neat.
Touch it, touch it.
Now, you can do it, but you're going to get shot. Okay?
Hear it.
Yeah, you can hear it. So now that after, it takes a while for this thing to go, we'll try it again. Now, it should have the charge build up a little bit more. So this is just basically doing what I do with the balloon, but on steroids.
Make sure you touch
the
it at full
electric
speed.
chair is
man.
on steroids.
Full speed is when you touch
So all it needs,
That's not really supposed to.
so all it needs to produce a charge is
No.
friction.
Yeah, and well, and a surface that can have the electrons either taken or put off. So if we do this,
What is that thing?
I would have done that
You
for
should've
you if
let
you just
him. I
asked,
know.
Burkamp.
It's
so if we're
That's
at the
gonna look so
grand
beautiful.
finale,
Ooh.
Octopus.
It's like the ride. You're like,
okay?
Wait, can I do that with my hair real quick? Bam!
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 look at them, they're stuck.
So if you touch those, will it shock you too?
No.
No, those are positively charged.
Wait, so why does that happen?
That's big.
Can you do
That's
that while
just
it's
a little bit creepy.
Can you do that while it's going so all of them follow your hand?
No, because nature doesn't like all the electric charge in one spot, so it wants to try and equalize that charge out. So as soon as I discharge it,
Look.
You want to careful.
Dang,
Hammer
with them
okay,
hands.
let's do it again.
It's like a little daisy.
So as soon as I discharge it,
Let me. Come on. Why do you
Okay.
always do that?
because I want to, that's why. So as soon as I give those electrons a place to go, then the electrons take that path of least resistance. It's no longer negatively charged.
Can I put my hand on it and see what it does?
Oh my gosh.
Like turn it on while.
Problem is,
Turkey like house
here's the only thing, and even like right now, if you put your hand close to it,
I'm not gonna push that button.
no. Even if you just put your hand close to it while it's going, you can feel the hair on your hand stand up.
Do your head. No. Your head. Do your
Oh, I'm
head.
getting every like
Reese,
shot.
do your head.
No, it's cool. It feels.
No, Reese, that's stupid.
No.
It's not.
Okay, let's try this. Kendra, you wanted to do a simple experiment.
Okay.
All you have to do is put your hand on it, like this, and I'm gonna turn it on, and hopefully...
Is it gonna hurt?
No, it won't hurt.
Do I need to take off my ring?
No, you're fine.
Okay.
Okay, so we'll do this. You stand on this.
No, wait a minute.
So
I
that
want to
you-
feel it. We'll be more than willing to do
Okay?
this.
Okay.
Okay.
I'm gonna put
So
my.
basically, you just put your hand on there. That's all you have to do. So basically, you're gonna be a life size of that.
Is my hair gonna go all up?
It might. The problem is it's really humid, and it works better if the air is dry. So it might.
All right, you guys. I'll take one for the team.
Okay, you ready?
This is for the video at Kendra Cunningham.
All right, now,
so
don't put your hand there.
You can't
Okay.
touch
Okay,
anything
you have to
else.
be isolated. Okay, you ready?
This is gonna go on video. Okay, go. I feel it in my foot! I feel it in my foot! You're crackling.
So, you can start to see her hair.
That was disappointing.
They went up. Look at the top.
Like, can you see?
Yeah. Her hair is following you.
Okay? So, it did work, but the problem is, it's just, there's so much humidity in the air.
Dude, if you do this, if you do this, like your feet start tingling. Like my feet were like.
Okay, because here's basically what's happening. The electrons are looking for the path of least resistance. So they're flowing over around you and not through you. And
Okay.
the Earth is like a huge sink. So those electrons are taking that path. They have no place to go on the end of your hair. So that's why your hair was standing up. Could you actually feel it?
I could feel it, but I could feel it a lot more in my feet.
Okay, all right. We got this. Good, grand, back we go. So if you look at this electrostatic force, it is the broadest of all of the forces. So if you look at everything that we did, Okay, the Van de Graaff generator. Okay, hey, it creates electricity. We can make electrons do a whole bunch of weird things. But it's also why we exist right now. If it wasn't for the electrostatic force, the universe wouldn't be here. Because if you think about it, for those of you that have been through Chem 1, what's one of the diatomic molecules? What's the simplest diatomic molecule?
Hydrogen.
Hydrogen. Okay? There's hydrogen, nitrogen, oxygen, fluorine, chlorine, bromine. Okay? So if you look at hydrogen, okay? Hydrogen is diatomic, right? There's always two of them that go together. So if you look at what happens here, if you think about it, it's pretty complex. So here's a proton, here's a proton. Here's a hydrogen atom, here's a hydrogen atom. Okay? So look, do these protons want to be near each other?
No.
No, they want to go flying apart, just like the strands of that hair did. Okay? They don't want to be near each other. At an atomic level, these things are really, really, really close together. So the repulsive force between these two protons is huge because they're so close together. Now, here you've got electrons that are flying around, right? What do the electrons want to do? They want to
Go around.
This is not biology. So the electrons don't want to be near each other. So why do they form a bond? What has to happen for that bond to form? What does nature gain from it? Because if nature doesn't gain anything from it, nature doesn't do it. What does it become? If I drop this, why does it fall? It becomes more stable, right? Nature hates potential energy. It does. I don't know, at some point Mother Nature and potential energy had a falling out. Maybe it was a Facebook post, I don't know. But nature hates potential energy. If you pull back a rubber band and stretch it, what happens? As soon as you let go, what happens?
It hits Reese in the face.
It goes flying. You hold something up, right?
Hey.
You let go of it, it goes flying. If I take this binder clip and pull it apart like this, as soon as I let go of it, it springs back. It isn't like nature goes, well, I'll think about maybe making it go. Maybe I won't. I don't know. I don't know. It's Thursday. So, no, it's immediately going to change from potential energy into kinetic energy. So, if nature is going to gain something from it, nature will do it. So, nature is going to form a stronger bond by taking these hydrogen atoms and putting them together. So, it's when you get inside the world of the atom, you can't overlay like what we call a macroscopic view. What happens in the atom is so weird, but it works beautifully from a mathematical model. So this guy by the name of Erwin Schrödinger developed what's called the wave function, and he described the movements of the electrons. And so basically what happens is that why that hydrogen bond is formed is because the wave functions overlap in the middle, and that produces something that's more stable. So if you look at what we as a civilization have done, the biggest thing that we've been able to do, and one of the biggest things that's allowed us to evolve, is that we've been able to control the amount of force that exists between atoms. I'll give you an example. You all, in this class, write with pencils, right? Pencil is basically, the pencil lead is graphite, which is basically nothing but carbon atoms. So think about this. So we've perfected a way to take those carbon atoms and make them stick together long enough to form graphite. Okay? So we've made that bond enough that they're going to stick together as pencil lead. But when you write on the paper, what happens?
Comes off.
It comes off. Okay? Because would it make any sense to carbon, if you rearrange it differently, you also get diamond, right? So would it make any sense to try and write with diamond?
Yeah.
No, it's just going to tear your paper, right? You're not going to strip bits of carbon off of a diamond, okay? It's the hardest substance in the world. So if I take carbon and rearrange it just right, I get graphite and I can write with it. So, but not only does that graphite get torn apart from the other bits of graphite, so that you can write with it, but it also has to stick with the paper. So it isn't like, hey, I write on the paper, I lift the paper up, and I shake it, and all the graphite comes falling off of it. Okay? It stays there. Now, let's say, God forbid, you've made a mistake. You erase it. How does the eraser work?
Never thought about these questions.
You've never taken a physics class before either.
It gets rubbed off on the eraser. And
Yes. So the attractive force for the eraser has to be greater than the attractive force that holds it onto the
Paper.
Otherwise,
It falls off.
it wouldn't come off the paper. Right? So even just that simple act, okay, of writing is very, very complex. You do laundry. Okay? What's the sole purpose of any laundry detergent? What does it do? Don't say it gets it clean. Okay?
It gets out the oil.
It gets out the oil, it gets out the dirt, whatever. So basically, if you think about it, the role of Tide, whatever that you use, is to break the bonds that hold the material to the cloth. But it's not strong enough, though, to break the bonds that hold the cloth together. It isn't like, hey, let's wash our clothes, and you dump it, you dump it in the laundry detergent, and you come out and all your clothes have dissolved. Okay? So it's a controlled breaking of bonds. You're breaking the bonds that form the stain, that hold it onto the cloth, but not enough to break the bonds that hold the cloth together itself.
That's why they're $1 million companies.
And that's why they're $1 million companies. Okay?
Billion.
Yeah, and so, but if you had soap and it isn't strong enough to break the bonds that hold it onto the cloth, guess what? You're going to quit buying it. But you don't want to buy something else that, oh, I'm going to sell hydrochloric acid as a cleaning agent, which it will, okay? But guess what it does to your clothes? Not so good, okay? So it's a balance that we have to strike. So basically, every substance, paper, tables, cloth, all exist because we have found a way to control the intermolecular forces that hold atoms together. Okay? That's, at the end of the day, that's what it is. So the electrostatic force is also cool because it creates electricity. Without electricity, imagine this. And don't pass out when I suggest this. What if we had never harnessed the capacity to store energy in batteries? How would you, let's say we'd still invented cell phones, but what if we had never invented the capacity to store energy in a battery? To make your cell phone work, what would you have to do?
Plug into a wall.
Your cell phone would only work if it was plugged into a wall.
That's just a home phone.
Okay? Yeah, that's a home phone, right? You can still be mobile, right? You can still plug it into the charger on your car, right? But that's the only time it would work if we had never developed batteries.
But your car has batteries too.
Yeah, but cars run on batteries too. So basically, we exist because of we found the different ways to harness this electrostatic force. What creates lightning? Just basically what we just did back there. Lightning is what we did with that Van der Graaf generator on extreme steroids.
But what comes with the force to do that?
What caused what?
What causes the force to cause the lightning? Like, how does it...
Basically, the bottom of the clouds become typically negatively charged, and so you have a buildup of electrons, and it gets so big that it finally just says, hey, and it sees the Earth as basically the easiest way out, and that's what happens. So that's the short version. There's ground to ground, there's cloud to cloud, there's a whole bunch of different forms of lightning, but that's a short version. So not only can it create lightning, but on a more subtle thing, we can use the same process to make toast. Okay? Hey, I want to, spot a toast in the morning, right, with my tea and crumpets. And so you put the toaster in, you push it down, this electricity flows through, it generates heat, the heat makes toast. So at the end of the day, we do a whole bunch of different things with its electrostatic force that allows us to have the existence that we do. Now, here's the odd thing. We really don't know why it does it. If you look at like electrons generating light, imagine if electrons, when the universe was formed, if electrons never had the capacity to generate photons. We wouldn't be here, we would not be here having this discussion. The universe could have still formed. You could have still had all of the matter, the energy, you could have still had stars, you could have had everything else. But that doesn't necessarily mean that you have to have light. So the fact that electrons can jump these energy levels and emit photons allows us to be here. And it's a cool deal. It allows us to get X-rays. It allows us to have microwaves. Well, I didn't mean to blow your mind.
No, I'm getting upset.
Why?
Because it all, okay, so you said everything is attracted to something. Everything should be a ball. Everything should be condensed.
No, 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 no. We're all neutral.
No, I'm saying that including with gravity, not just electromagnetic forces,
Yeah.
it should all just be compacted.
But thankfully, so here's the deal. We exist because that gravitational constant has a fixed value, 6.67 times 10 to the negative 11. We'll talk about that number later. But if you think about even that constant, when you look at the formation of the universes, if you subscribe to the Big Bang Theory, okay, not the show, the theory, which is a good show, by the way. But if gravity had been stronger, if that gravitational constant had been a bigger number, you would have had the Big Bang, and then you would have had the big crunch, okay? If gravity had been weaker, we wouldn't be here having this discussion either. Because all of the complex particles that exist on the periodic table and make us all up were formed from stars, okay? The only element that existed in the universe at the beginning was hydrogen. You had gravity, it formed the stars, you had helium, those exploded, then you started to form lithium, carbon, okay? And then you blew up the next generation of stars, and that's how you got the heavy metals. So we are literally, it sounds very 60-ish and like we should all sing Kumbaya, but we are all made of stardust. Every complex atom that exists in your body right now, at some point had to be formed in the inner core of a star. That star exploded, those atoms got spread out, they reformed. Here we are in MG,
What if
Mays
matter
High School
has
talking.
brains and they have
So
minds?
here's my point. If gravity had been weaker, the stars would have never formed, and the universe just would have continuously expanded, and you would have never got stars. Without the formation of stars, we don't have this discussion either. So it's kind of, so we'll finish this up tomorrow.